This video covers two aspects of water. One is the salinity of the oceans, how salty are they? And the other is a unique property that water has called hydrogen bonds. Oh, here are some sharks. Students often think when we talk about oceanography, we're going to talk about sharks, but we don't. So here's a little fix for you, some nice pictures of sharks. You've already seen these learning outcomes in video 7b.1. This is 7b.2. Although two of them were not on there. And so I've highlighted them in yellow. And this particular video is going to cover point 6 about salinity and point 9 about hydrogen bonds in water. So let's get started with salinity. Salinity is the amount of dissolved material in water. So if you have something in water that hasn't dissolved yet, like a big chunk of salt, that wouldn't count towards salinity. What we have here is a little cartoon showing 1 kilogram of water. And remember, 1 kilogram of water is the same as 1,000 grams. It's also 1 liter. And out of the average seawater, 1 kilogram of water will hold about 34.8 grams of dissolved material. What is that material? Well, it's mostly chloride and sodium, but it's also sulfate, magnesium, calcium, some other ions. And in fact, probably every element of the periodic table is in the ocean to some small extent. So if we have 34.8 grams in 1,000 grams of seawater, that's 3.48%. Now, if you look over here, I have typical salinity is 3.5%. So I'm just taking this number and rounding it up. Or 35, and then I have this symbol, which is called per mil. So percent is out of 100. I think you guys know that. Then per mil is parts out of 1,000. And we use this when we talk about ocean salinity so we can drop the decimal. It's just a little more convenient. So 25% is equal to 250 per mil. And you can see if you look at the fractions, these really are the exact same proportions. They're each a quarter of the whole. 3% would then be 30 per mil. And 3.5% would be 35 per mil. On average, as I have up here in pink, the ocean salinity is between 33 and 38 per mil. We've already talked about the processes that can change salinity in the last video, talking about adding fresh water from melting ice or glaciers. We talked about adding water from runoff of rivers or increasing the salinity by evaporating fresh water. Here's a chart that summarizes all of this. What we have here are the processes involved, and then whether they decrease or increase salinity here, and then a little bit more about how it's accomplished in the details. So this is a good summary to review before your next exam on processes that change salinity. They either make water in the ocean more salty or less salty. Here's a comparison between pure water and seawater. Some of these are kind of interesting. Both of them have a clear color when they're in small amounts and a blue-green color when they're in large amounts. And that's because water molecules tend to scatter blue and green wavelengths more than the oranges and yellows and reds. Fresh water is odorless and tasteless, whereas seawater is distinctly marine and salty. The pH, or the acidity of water, is 7 for pure water and somewhere around 8 for seawater. So actually seawater tends to be a little more alkaline than pure water, and we're going to talk about that feature in the next video. The density of ocean water is also higher than pure water, and that's because the salts add some mass to the water. The presence of salt also decreases the freezing point and increases the boiling point. This is an extreme example of how salt water is dense. This is the Dead Sea, which is a region that has a lot of evaporation, and so the water has become very concentrated in salts. It actually has 33% dissolved material in it, or 330 per mil. So this person here is floating naturally without anything underneath holding her up because the water is so incredibly dense. So how does this change throughout the Earth? How does water's salinity vary? Well, if you look at this chart here, we have latitude on this side of the graph with the equator here and north latitudes above, south below. And then in red, we have the average temperature of the water. So it's coldest near the poles, it gets warmer and warmer towards the equator, and then it gets colder back at the South Pole, and that's expected. In the green, we have the values of salinity in per mil. So there are some low values in the north of maybe 33 per mil. It increases to about 35 or 36 per mil, and then it dips down at the equator and dips back again at the Tropic of Capricorn to make this kind of big zigzag shape. So why is it that where we have the warmest temperatures at the equator, we don't have the most evaporation and the most saline waters? Well, if you remember, the equator is a low pressure belt, and low pressure means rising air, which means rain. So there's a lot of fresh water entering the equatorial waters to lower the salinity. On the other hand, at 30° north and south, we have the subtropical high pressure belts. And if you recall, that's where air sinks. We have very dry conditions, lots of evaporation. And so fresh water gets evaporated, so salinity is at a maximum around 30° north and south. Okay, now we're going to move on to water. I think most of you know that water consists of two elements, hydrogen and oxygen. H2O is how it's written, and you'll often see the water molecule illustrated like this, with the O and the two H's sort of on the same side of the O, not really spread apart. Now, why is that? Well, it has to do with the geometry of the elements that are binding in the molecule. And we don't have time to go through this in detail, but for example, in carbon dioxide, we have a carbon atom, and the oxygen atoms are 180 degrees away from each other as they bond to the carbon. That's a very stable energy for the electrons. Water, if you were going to take an analogy, might look like this, but it doesn't. Water actually has the two hydrogens kind of closer together instead of spread out at 180 degrees. So why is that? Well, let's look at the electrons in these atoms. So here's an oxygen atom, and the blue dots are electrons, and then here are two hydrogens. And both, as I said earlier, of the hydrogens are sort of on the same side as the oxygen. They're separated by about 105 degrees. And the reason is that the electrons that are not binding to anything, which are the non-bonding electrons up here in the oxygen atom, tend to push away from each other. And as a result, I have a different sort of picture, you wind up forcing these hydrogens closer together. So this is a good cartoon. Here's the oxygen, here are the hydrogens, and then these little bubbles are showing the two electron pairs. And so because these two pairs of electrons are repelling each other, it winds up forcing the hydrogen atoms on this side. So the net result is that one side of a water molecule has a small negative charge, and the hydrogen ends have a small positive charge, and this means they are dipolar. So you'll see cartoons of water molecules, and you'll often see a negative and a plus, as are shown here. And here's another type of cartoon showing how the two hydrogens are closer together. So this polarity, this dipole polarity, means we have a little negative charge at the oxygen end and a little positive charge at the hydrogen ends, and then negatives and positives attract each other, and so we actually have what's called a hydrogen bond between different water molecules. Now, the bonds that are connecting the hydrogen to the oxygen in a single molecule are covalent bonds, and they're very strong, and we'll talk more about them when we talk about minerals. But these are hydrogen bonds, and they account for lots of very unique features of water. First of all, they account for the fact that snowflakes and ice are six-sided. So here's a little cartoon showing a bunch of water molecules, and I'm going to focus on this one right here. So remember, we have a little plus where the hydrogen is on this side, a little plus on this side, and a little minus on that side. So what's going to happen is those are going to attract the opposite charge. So this one is going to kind of line itself up with this molecule's positive side, and this positive one's going to line up with this one's negative side, and so is that one. And so you wind up with this three-pronged geometry that when you look at a lot of water molecules, wind up making a six-sided geometry, which is shown here. And that is the reason why ice and snowflakes have six sides. Another thing that the hydrogen bonds do is they make it very easy for things to be dissolved in water. Water is sometimes called the universal solvent because things dissolve in it so readily. So this is a structure of salt, sodium chloride. And when it's broken down, the chlorine atoms become negative ions and the sodium atoms become positive. So as they're broken down in water, the chlorine atoms that are negatively charged wind up being surrounded and isolated by the positive ends of the water molecules. Conversely, the positive sodium ion winds up being surrounded by the negative ends of the water molecules. This phenomenon also explains something called surface tension, and you might have seen little bugs that seem to walk on water. And that's because if you think about what's going on at a surface of water, here's a water surface and it's shown in two different ways. Inside the water, a glass of water, for example, there are forces pulling on each water molecule by all the other water molecules in all directions. But at the surface, there's an absence of force pulling in the direction towards the air. And so what happens is it makes these water molecules slightly stronger, and they pull on each other and they almost make a thin skin on the surface of water, which is why you can overfill a cup of water, because they're adding extra strength because of those hydrogen bonds. Another property that's similar is called cohesion. So water droplets can make these round balls. Not many liquids can do this. If you think about like rubbing alcohol or oil, they tend to be flat. And that's again because we have at the surface the hydrogen bonds holding each other and keeping that skin of the water coherent. Adhesion is when the water's hydrogen bonds are actually attracted to something that has another electrical charge. And it turns out glass has a slight electrical charge. And so what happens is that the water gets pulled upwards by the glass. It's called a meniscus when we're looking at something very skinny like a graduated cylinder. And that's water being pulled upwards. It's also why water clings to leaves or branches, such as in this picture. So cohesion is between two water molecules. Adhesion is between a water molecule and something else, and they work together to climb up the edges of a glass. Finally, just a summary, hydrogen bonds are uniquely strong in water, and they are the reason for six-sided snowflakes, surface tension, cohesion, adhesion, and also capillary action that sends water up trees from the roots to the top. And this is shown with some cabbage leaves here as colored water makes its way upwards.